Hey everyone, thank you so much for joining. My name is Eric, and in this video, I'm going to show you how to use Python to generate these cool looking solar system images. Now this project is a type of generative art. If you're not familiar with that term, it's the output of a system that makes its own decisions about the art piece rather than a human. That system could be as simple as a single Python program, as long as it has rules and some aspect of randomness. I think this project is a great place for someone to get started with generative art. Just looking at the two examples that I'm showing you here, you can see the two main aspects of randomness that we've introduced to the system. If you imagine that these are actually solar systems, then you can see that we're randomizing planet size and planet color. Just allowing those two things to be random makes for some pretty cool looking results. There are other things in these images that are not random that we can change, such as if you look at the image on the left, you can see that it's got these straight lines for the orbits rather than an actual circular, or you could even make it elliptical. That's more of a stylistic choice. I just personally kind of like the lines more. On the right image, you can also see that there's this mass that's supposed to represent, some central celestial object. It could be a star that the planets are orbiting. And the one on the left doesn't have that, and again, that's just a style. I actually added that as a user option or argument rather than something that's random, but it could be random. That's the cool thing about this project. It's almost like a great foundation, and if you follow along with this video and you like what you see, you'll be able to build almost whatever you want. You can add a lot more variability to the planets with things like multiple colors, different shapes. Maybe even if you're ambitious, you could add an asteroid belt. I think that would look very cool. All that to say, I'm super excited. I hope you are. Without delaying any further, let's get rid of these and we'll start taking a look at the code. So the first thing we have to look at is the third-party libraries that we'll need to make this program happen. We don't need a lot, and I'll have to put some links in the description to those libraries so you'll be able to download them. And I'll also add, oops, that is not big enough. I would say let me know if you guys can see, but I know that you can't really respond. Okay, hopefully that's pretty good. I'll make it a little bit bigger. Import. Hopefully that's okay. I will post, just in case there's things that people can't see, I'll probably post the code, so I wouldn't worry too much about following along with every keystroke. Although I do encourage you to do that just for your own understanding of the system. So back to what I was saying before, there's a couple third-party libraries that we'll need to have installed and import into this project to manipulate the image. Those two things are PyCairo, which allows us to do vector art in Python, and then Pill or Pillow, which is a simpler image manipulation file that we're going to use to apply a kind of grainy texture to the images. And we'll look at that close to the end of this program. So those are the two third-party. So we're using this argparse. We're importing argparse to take in command line options for the script. I don't think that's a third party. I think that's included. I'm going to make sure on that after I finish recording. We have to import math, import random. I think that's everything. So we've imported all of that. From Peel, we need to import image and image draw, and like I said, we'll use those at the end to apply a grainy texture to the program. So I'm going to start off, I wasn't sure how I wanted to kind of organize this, but I'm going to start off in the main and we'll go from there, and if I need to move things around I will. So with this argument parser, argparse, that we've imported, if you're not familiar with this, it's a really simple way to add command line options so that you can, well, the best thing about it to me is that they can be optional, which is really cool. You don't have to worry about providing defaults if you don't want to. So we're going to define quite a few arguments for this project. So we need to create a parser. Parser equals argparse dot argument parser. I'm going to use that parser to, I think all of these are going to be added with add argument. I feel like there's another option that you can actually use, but I don't remember what that is. So we're adding this first argument, parser.add argument. My mind went blank for a second. We're adding width to begin with. So the way that this, you'll see kind of the structure of how this works. We define the, I'm not sure exactly what it's called, the tag or the command line kind of identifier for the variable. We can add these help, let's see, specify width. Basically, if you forget how to use the program, then you can ask for help and it will show you the descriptions for each of the command line options that you've created. So we've got width, specify width, then we need a default just in case you, like I said, these are optional. So if you don't provide anything, we still need something there. We're going to say 3000 and then type equals int. So that's width. I'm just going to go down the line here, argument. So we need a width and a height for the image, and that's pretty self-explanatory. It's just going to create the resolution of the image. Specify height. I realize that's not very descriptive. Default equals 2000. So I think, yeah, the default is kind of a landscape result. Parser.add argument. So this is where it gets kind of interesting. I showed you the differences between those two images where one had an actual orbit and one had kind of the cool looking lines. I say cool looking, you may not think it's as cool as me, but these are the options that are going to allow us to do that. So you can either pass in orbit, orbits. You can either pass in an orbit tag or a line tag, and those are just Boolean values. So action equals store true. So if you include that tag, then that variable, once we parse it, will be true, and we'll know that you want to use actual orbits. Argument dash L dash line. The reason I'm defining two of these, the dash O, the dash dash orbit, is just because it's just your own preference. It's basically a shortcut if you want to do the dash H or a dash L or dash O. Help. I'm gonna stop putting the helps because we're not really concerned with that. So action equals store true. Parser dot add argument. The next piece is sun size. So the image on the right that I showed you to begin with had a sun, the image on the left did not. That's because when I ran the image on the left, I gave it a sun size of 0, so the sun didn't appear. And that's something you can make random if you'd like. I'm showing a little bit of my ignorance because I may just be able to leave the help out completely. I'm pretty sure I can do that, but I'm going to stick with what I've been doing for no reason. So we've imported random into this project, and this is our first time using it. For the default for the sun size, if you don't give it anything, just so we can have a little bit of randomness, it's going to choose a size between 200 and 400 for the sun. That just allows it, I guess that's the first example of chance in this system, which is pretty cool. So 2 more things. We're almost there for the most boring part of this video that's taking the longest amount of time. Border size. You saw the two borders. I think they were actually the same size in these examples that I showed, but you could make it a lot thicker. You could get rid of it completely. That is definitely up to you. The default is set at 50, type equals int. And then the last one, thank goodness, argument is noise. This is one of the cool ones. So it was hard to tell. It'll be easier to tell at the end, but each of these images actually has kind of a texture to it, and that's achieved in a very simple, in my opinion, neat kind of way. We'll actually add one for that texture. Default equals 0.4. So the way that that's done is each pixel in the image is actually changed in color by just a very small amount. So it either gets a little bit darker or a little bit lighter, essentially, which is cool because it's applied to the R, G, and B values. So it gets a little bit lighter, gets a little bit darker across the whole image. So it creates this neat little texture. I like it a lot, and you can raise and decrease that intensity. You get rid of the texture completely, but getting rid of it just doesn't look very good to me. What am I need to stop talking and just type because I'm not even paying attention. Type equals float. Okay, so that's it for the arguments. Args equals parser dot parse. This wasn't supposed to be a arg parse tutorial, but hopefully that's actually, I think, a pretty good example of how to use this. So we've got these arguments. Now we need to get them from the user. So we'll say width height equals args dot width args dot height. Actually, I needed, just in case. Border size equals args dot border size. Sun size equals args dot sun. Oops, size. And then sun. So this is where we start deviating from the args parse a little bit. So where we're starting, where the program starts, is at the bottom, and it kind of builds itself towards the top. So we're going to start wherever the sun is created, and then we're going to make each planet kind of iteratively. So we're starting with the sun. So we're going to define a sun center, and that's as simple as the height minus the border size. Hopefully that makes sense. If you have a border of 100, then the sun has to move up in order to still, you don't want the very tip of the sun pointing out. So I kind of align the sun center with the edge of the border. So sun center is our starting point. Now we're going to define our image manipulation objects. So IMS, our image surface, we're going to call Cairo dot image surface, Cairo dot format RGB 32. That basically lets us apply some alpha values to each pixel, width, height. So Cairo, I think that's right. Image surface, and then our final kind of image object is going to be the CR equals Cairo dot context IMS. So now that we have that image object, we have the ability to manipulate the image however we want. We can draw vector objects, we can draw squares, which may also be vector objects. But we need some functions in order to help us do that. And I'm going to make that first function right now. So I'm going to define draw background CR. Now I'm defining these arguments. Draw background is not a Cairo method. We're going to define that function. I'm just adding the arguments now so you can kind of see width, height. So CR, we're passing on that image surface, which is what we'll use to actually draw. 0.3, 0.3, 0.3, those are the RGB values of the background. For some reason, Cairo likes it to be in this 0 to 1 float value, which is fine. And then width and height, we're going to draw the background over the entire image. So I'm going to come up here. We're going to add our first function, which is draw background. We're taking in the CR, the Cairo image surface object. We're taking in R, G, and B, width, height. And it's 3 lines of code to draw the background. So cr.set source RGB, RGB. So we've set our color, cr.rectangle. PyCairo makes this super easy. Draw rectangle, we're giving it 4 coordinates. It's going to be, or actually we're giving it 2 coordinates, 2 points. We're giving it 4 values to define those points. So 0, 0 is kind of the origin. That's the top left of the image. And then we're going to draw a rectangle all the way to the bottom right of the image, which is width, height. Hopefully that makes sense. Now that we've drawn the rectangle, we can fill it with our source RGB. I think that is everything for draw background. And that's going to be very similar to our process for the rest of this stuff. Let me get us a little real estate here. So, draw background. I think that looks pretty good. Man, I'm already realizing how long this video is taking. My counter, I'll have to edit some stuff out, but I'm already getting close to 20 minutes. So I hope you guys are enjoying this. I hope you're sticking with me. It's going to be really cool when we get finished with it. Moving on, we're going to define our sun color, which is actually going to also define our border color. Sun color equals random.choice list of colors. Now, list of colors is something else that we have to define. It's just going to be an array of these RGB values that can contain any you want. So when I first started working on this project, I actually made it where the colors were completely random, but it just didn't look very good in my opinion. I couldn't really get behind it because there's so many colors. I mean, it's just, and it was difficult to just let it run free and have it look appealing almost at all. So I'll throw in the list that I created, and if you're following along, I encourage you to make your own list, figure out the colors you like. I just kind of went through and picked out a lot of different colors that I thought when I added them it looked pretty good. A lot of blues, a lot of reds, a lot of greens, but definitely not completely random. So there you go. That's sun color. Now, because we have to pass in RGB values as floats, we need to actually convert this to float values. So sun R, sun G, sun B, sun color. Now this is a pretty cool little deal. We're gonna pick the first value of this sun color. Now remember, we're passing in this kind of tuple or this truple, this RGB value object to sun color. So it's got 3 values in this variable. So we're going to pull out the first one and we're going to divide it by 255.0, and that's going to give us the float equivalent of that red value. And we're going to do the exact same thing for blue and green. I think that is all that we need. Now that we have the sun R, G, and B values, we can actually draw the sun. So draw circle, and this is another function that we're going to have to define. So this will be very similar to draw background. We're going to say draw circle fill CR width divided by 2, sun center, sun size, sun R, sun G, and sun B, RGB. So those are arguments for this draw circle fill. The reason that I sent, let me see, actually I think I did something wrong. Sun center. Oh, no I didn't. Okay, width divided by 2. So we have to define this. It's like I said, it's going to be very similar to draw background, draw circle fill. CR, the width divided by 2 was to get our X value for the sun centered, and we're going to use that for pretty much all these planets because they are centered. They don't have to be if you'd rather do something else. I encourage you again to do that. So we're passing in X and Y. Radius is actually the sun size, and then RGB. So we have to do the same thing that we did in background. We have to change the color, set source RGB, and RGB. Pretty straightforward. And then instead of drawing a rectangle, we have to draw an arc. X, Y, radius, 0. I gotta be honest, I'm not exactly sure what the 0, I think the 0 is the weight of the border, possibly. I'm not 100% sure on that. And then our final argument is 2 times math.pi. So 2 pi r is basically what we're doing to create an arc that is an entire circle. Even though it only really has to be a half circle, but we're going to use this same function for our planets. And then CR dot fill, just like the background. Okay. Again, I want to apologize for my kind of disjointed method. This is not at all the process of how I originally developed the script, and it's taking a lot more out of me than I thought it would to walk through it in a better way. So I feel like I'm struggling a little bit, but hopefully things are making sense and you're still interested and I haven't scared you away yet. Moving on. We've got draw circle fill for creating the sun. We're going to use that later for the planets. Now that we've created the sun, it's a good time to start defining some of the constraints to the system. So we don't want planets to be touching each other. We certainly don't want planets overlapping each other. And so that's one of the first values we can play with. Distance between planets. I gave it 20, which maybe that's not enough. You could try more, you could try less. I'll leave that up to you. We need to keep up with where our last planet was. Last center equals sun center. I'm defining the sun as a planet for right now just to get the process started. And then we need to also keep up with the last size. So last size equals sun size. Those are the constraints on where the planets are going to be created. And now we can start introducing random aspects to the creation of the size themselves. So the size constraints for the planets actually increase over the course of the program. We'll start off with size equals to 5 and max size equal to 70. The last thing that we need to keep up with, actually I forgot one, last color equals sun color. So we've got all of our previous information, min size, max size, and now we've actually gotten to get into the kind of the nitty-gritty of this algorithm. I'm going to try to get through this a little bit faster than how I've gotten through the rest of this video. So for x in x range 120, next size equals random.rand int min size max size. So we've defined basically the size of our next planet. Next center equals last center minus last size minus next size times 2 minus distance between planets. So next center equals last center minus last size minus next size times 2 minus distance between planets. So that's where the next center, or the next planet, will be centered. If not next center minus next size, oops, less than border size. Now this is interesting. We're making sure that we haven't expanded all the way to the top of the image. So you could give it a really short height, and once we get to the point where our next center or our next planet is overlapping with the border, we're not going to create it. So that's what that means, if not. And now we're actually going to start using some of our arguments. So if args.orbit draw orbit, this is another function that we'll have to create. So draw orbit CR. 4 is going to be the line width of the orbit. That's another thing that I would highly encourage you to make random. I just picked 4 because I think it worked out well. I tried less, I tried more. I think it looks pretty good, but you can play with that. Width 2 for the center. Sun center. So this is interesting. The sun center will always be passed in when drawing orbits, because that's literally what the orbit is orbiting. So that's going to serve as our center for every orbit, which I think is cool, because even though we're writing programs that are generating these kind of 2D solar systems, it's following the exact same rules. It's literally orbiting the sun, which, I don't know, that's just interesting to me. Next center, height minus next center. Actually, we need a little bit more. Height minus next center minus border size. And then 0.6, 0.6, 0.6. Okay, so if it's not orbit, elif args dot line, we want to do the lines instead, then we're not actually going to call a function. Now I'm going to do the line, and then we're going to go back and we're going to make the draw orbit function. So cr.move to border size times 2 next center. So we're moving. When you're drawing a line, you kind of have to change where your origin is, which is kind of interesting to me. Line 2 width minus border size times 2 next center. cr.line 2 width minus border size times 2 next center. Okay. cr.stroke. So we have to use cr.stroke instead of cr.fill, just because we're drawing a line and we're not filling up a shape. So that is kind of the logic behind orbit and line. Now we need to go up and we need to create this draw orbit function. Very similar to draw circle fill and draw background. Draw orbit cr line width origin radius RGB cr.set line width. Now this is a piece that I kind of messed up on my design. I'm actually passing in a R, G, and B value, but I'm not using them because I'm leaving the color or the source RGB set to the last planet's color. Just because playing around with it, I think it looks a little bit better 2 times. But if you wanted to switch back to the old way, then you could definitely do that. Stroke. And you can define your own orbit colors. If you don't think the orbit color should be the same color as the planet, then all you would really need to do is set source RGB to this RGB value. I'm starting to worry that I've made a mistake because I see that some of the formatting has actually gone away from these functions, but we will see what I have done when we try to run this. So, okay. If not, next center minus next size. So we're done with the orbit and the line, hopefully. Now we're going to move on to drawing the planet. So we've drawn the orbits, but if you imagine drawing the orbits without the planets being there, we've got a complete orbit. And I actually need to pop back out and show you the image. I'm going to pull up this example again. If you look at the way this looks and you look at what we've done so far, we've drawn the size, or we've drawn the sun. We've drawn the border. Have we drawn the border? We haven't drawn the border yet. I'm sorry. We've drawn the sun and we've drawn the orbits. But if you look at the way that this is kind of designed, the orbits aren't actually touching the planets. But the way that we've done it as of right now, that should be connected. So we need to figure out a way to get rid of these little sections just because it looks a little bit better to have those connected. And you can see what I was talking about where the color of the orbit corresponds to the previous planet. So what we're going to do now is actually draw a circle fill with that function we defined. And we're going to draw it such that it deletes basically a part of that orbit that we just created. So we're just going to give it the same color as the background. It feels a little hacky, but it definitely works. So size times 1.3.3.3.3. So that's our background color, and we're increasing it by 1.3. It's scaling with the size of the planet. That way the differences, if I pull back up that example, this is a larger planet than this one, so the space between the orbits is a little more pronounced, as I think it should be. So let me maximize this again. So, and then the color of the background. And we've already got that function defined, so that should be good. Now we need to pick a new random color for the current planet. We've been relying on the color for the previous planet. Ran color equals random.choice list of colors, while we don't want the colors to repeat right beside each other. It's okay if they repeat throughout the output, but we don't want them to be right next to each other, especially because it just doesn't look good. It might look good to you, and if it does, I encourage you to remove this, but and color equals random.choice list of colors. So we're using that same list of colors that we defined before. And then we need to remember to set last color to our color that we have finally chosen. So it's going to repeat until it picks a new color, and then we're going to set last color. And then we need to actually do the same thing that we did to the sun's color. Convert them to floats between 0 and 1 for the pi Cairo. And color 2.5.0. Okay, I think that is right. And now we just need to draw the planet. So draw circle fill CR width. Remember, this is the origin, so we're in the middle and we're at the center of this next planet. We're gonna give the arc, or the diameter. Actually, I'm sorry, I think this is the radius that we're giving it with next size, and then the RGB that we just chose. And now we're just updating our kind of control variables. So we're saying last center equals next center as we're getting ready to loop back, or loop to our next planet. Last size equals next size. And this is a cool part as well. So we started off with a minimum size of the planets and a maximum size of the planets, but we actually want to increase those each time. So what I did was min size plus equal to 5. And for max size, I said plus equals to 5 times x. And remember, x is our value for iterating through a maximum of 20 planets. You could actually increase this if you want. So we've got x. So as we get farther along, the chance for the planets being larger gets higher much faster than the chance of the planets being smaller, if that kind of makes sense. I wanted the planets to get larger on average, but I still wanted a chance for kind of an outlier of this really small planet. And that happens in some cases. So you can play with that as well if you want to change how those planets grow. So we've done that. We've got all of this. I think that is almost everything. Actually, I have made a critical error. All of this, 100% of this code, is actually supposed to be tabbed or spaced into this if not area. It's supposed to be underneath this entire logic. So that could have been bad. That's actually supposed to all be in there because we shouldn't be drawing the planet if we're interacting or intersecting with the border. So, but we're coming out of that loop or that logic now, and we're coming back up to this level. So I think that's right. So we've drawn all the planets, hopefully. So now we can draw the border, and this is another function that we'll need to add. Draw border, CR border size sun R, and we're using the same color that we defined for the sun. Sun B width height. Okay. As far as the image goes, it's drawn. It should be available. Now it just has to be saved, and we're going to add that texture that I talked about. So we have that image object that we set up before. This right here, this image surface. That's actually what we're going to use to save. So we're going to say ims.write to PNG. And we're going to call this generative space example. Usually what I like to do is set up an example folder, and then I will use the arguments that I provided. I'll append them somewhere in the name for the file itself. That way when I create a file, it gets written to that example folder, and each image is automatically unique. That way I can have a ton of different examples without always having to regenerate them. But for this example, we're just going to say generative space example.png. We've written it to the PNG. So I think that's it. I think it should be in there. Now we're going to move away from PyCairo. Oh, I am really blanking on this. We haven't made our draw border function yet. So we're going to come up here and we're going to add our last additional function. Def. I'm getting really worried about this function because the colors are not helping me out much. Draw border. CR.size RGB width height. So for this, we are going to change to this new RGB that we passed in. CR.set source RGB CR.rectangle. It's pretty simple to imagine the logic behind the border. We're just drawing 4 rectangles around the edges. So, and they change depending on our image width and height and the size that we have specified for the border. So we start off in the top left, and we're going to go to size, height. So we're going to the bottom left of the image, basically. This is the left side of the border. CR.rectangle, rectangle, 0, 0, width, size. So this is the top part of the border. CR.rectangle, rectangle, Man. Rectangle. 0 height minus size. So this is the top left of the bottom part of the border. We're going to take that, we're going to go to width size. Is that right? I'm having trouble working through this logic. cr.rectangle width minus size 0 size height. Okay, I think that's right. That should be correct. If it's not, we'll find out. And we'll fix it. Okay, so we've got draw border. That should work now. We've written to an image. Now we need to open this image in Pill or Pillow. And we're going to add our last little random aspect, which is the texture. So Pill image, this is just a new object or variable. Image.open generative space example.png. So we're opening the image that we just created. As soon as it's been created, we're going to edit it again. We are going to load the image. So we're basically getting a large array of every pixel. Peel image.load, and then we're going to iterate through those pixels. Let me get through this, and then it'll be a little, hopefully it'll kind of make sense. J in range, peel image.size. So we're iterating through, it's basically a matrix of pixels, peel image, and we're iterating through them. But the colors are stored in the pixels object. So pixels j. So we're basically pulling the color values, and we're going to apply some noise to those. So we need to define one more function, which is float gen. We're actually going to pop up here, and we're going to do that first. So if you're not familiar with Python Lambda Functions, we actually don't have to create a function on its own. We can do this cool little deal. I'll just walk through it. Equals lambda a b random.uniform a b. So we've defined this lambda function to return. It's going to take in an a and a b, and it's going to return random.uniform, which is basically, it's going to pick a random float value between these two values. So float gen is basically the name of that function, and we can call that just like this. So float gen, and we're going to use 1.0 minus args.noise. Remember, we passed in a float value to specify how much noise we wanted, and we're going to use that to create this kind of range of noise to apply to our pixels. So pixels, oops, j, man, I am losing it. In this part, we're applying the noise, and we're casting the RGB values back to ints, because pillow is different than PyCairo, and it'll actually take an int value for the colors. So int r times noise. It's interesting to think about. We're either decreasing the intensity of the color or increasing the intensity. So it's either getting closer to black or closer to white, which is, it's interesting how simple it is, and it's also interesting how well it works when applying these textures. It would be the same thing as putting a filter over the image to make it look textured. I think it works pretty well. You can play with that. So we've done that. Pretty straightforward. Peel image.save. And we're going to save it I'm going to save it to a different spot, actually. Space texture.png. So since we're doing that, let's actually change this to generative space flat and flat. And then, so that'll be flat, that'll be texture, and you'll kind of see the difference. And then the last thing we need to do, of course, that I probably should have done at the beginning is we just need to call the main Python function. So main Okay, I think that should be everything. Let's give it a try. I hope it works. I think it should. We'll give it a shot. So I'm gonna pull up my terminal. Hopefully you can see this. I'm in the directory where I have the Python file created, and I'm just gonna call it, and I'm gonna pass in our arguments that we defined here. So terminal, and also in case you're using a virtual environment, I've activated my virtual environment because that's where I have my PyCairo and my Pillow installed. But Python generative space system.py. So the rest of this is optional, but we're going to give it width. We're going to say 3,000. Let's say 3,500. Oops. Man, I tell you what, height, we'll say 2,200, just to, I don't know, just to play around with it. I do want to do line, so I'm going to say I'm not passing in -O, I'm passing in -L. For sun size, to begin with, I'm just going to do 0. I don't know. I'm just going to leave it at that. And then border size, I'm going to say 50. I think that's the default anyway. And then for noise, I'm going to do 0.4, which is also the default, but I think it works pretty well. So we'll see if this works. And of course it doesn't work. Def draw. Oh, okay. That's a pretty easy fix. And that was our problem the entire time. So we need these, which I forgot. Hopefully you probably caught that in the video, but easy enough. Okay. Second time's the charm. Second time is not the charm. File generative space system line 114. Draw global name. Width is not defined. No, it is not. 114. Oh. Let me pull back up my... Where is this? This is line 114, line 90. What if? That makes sense. So we fix that. I think the debugging part of this is important. I thought about maybe editing this out and just making it perfect and streamlining and everything, but I don't think that's very realistic. And I think a hour-long video on how to make this program is a little bit more realistic. So let's try it again. Third time's a charm. Third time really is a charm. I think it's actually running. So it does take a little while, mostly because we're editing each pixel individually. So you can imagine that takes a decent amount of time. If you do a much smaller image, it could happen almost instantly if you don't edit every pixel. So it finished. We're back. Let me pull up my examples folder and we'll see if it's in there. Or we'll see if I didn't put it in that. Okay. So, okay. All right, we did it. So here is our flat. I'm showing you the flat to begin with. That's our flat image. I think it looks pretty good. I think it worked out pretty well. Everything looks like it worked. Now, one thing I'm going to do, I'm going to go ahead and do is I'm going to regenerate it. We're looking at the flat. I'm going to regenerate it. You're actually going to see it change. I think yeah. So the flat happens almost instantly because of just how fast this is. The rest of the processing is happening to the textured image, which I will show you in a second as soon as it's finished. In hopefully pretty soon. Okay, so it's finished. Now I'm going to pull up the textured image and you'll be able to see. Let me minimize this one a little bit. you'll see how much better it looks. Yeah, I mean, that looks, I don't know, it's hard to explain. I guess it's a way of almost faking complexity, because this image over here looks cool, I guess. Like, I mean, you can still have an appreciation for the randomness and the colors, and you may like it more. That's fantastic. It's very minimalist. But this, in my opinion, it just looks a little more complex. It feels a little bit better. It looks like you could actually touch it and feel it. For posters, I've got a couple posters of this put up, and they just look really cool. It looks, I don't know. That's up to you. It's personal preference, but you can see the difference. But it is cool to see that image generate almost instantly. But this one, it takes a while to come through and actually save. So the last thing that I would do, since we spent so much time on this, I'm going to run, I'm going to just stop that process. So I'm going to run the same thing. I'm going to increase the noise value just to show you. We're going to increase it to 0.8 just to show you kind of, you know what? Actually, I keep changing my mind about this. We're going to leave the border the same. We're going to add a sun of 200. We're going to change to orbit. And everything else is going to be the same. But we bump the noise up just so you can see kind of the key difference of what that looks like. So this is what it looked like before. And when it finishes, you'll see a pretty drastic difference. The flat back there, again, it's just your own preference between the line and the orbit. But it is cool to see the orbit working perfectly. So it's finished. And there you go. So a 0.8 texture. The texture is a little bit more pronounced, but I think it looks pretty good. I think if you enjoy the sun being there, some of my suggestions would be to just make it larger. Something I played around with a little bit was not putting the sun center here at the border edge, but actually putting it much lower below the image, and then making the sun this massive, just crazy large object, so that the edge arc of the sun actually extended across the screen, and then your planets are truly dwarfed by this large sun. That's something to play around with. You can play around with these colors. You can play around with the line width. Play around with the background color too, because I haven't really done that much. But I think that's probably all I should. That's probably where I should stop, because this video is literally about to top out at over an hour. I put you through a lot. I took code that was barely over 100 lines, and I'm pretty sure I feel like I spent I spent a lot of time on almost every line. I hope it was helpful. I am going to post the code so that people will be able to access it. Hopefully you still watch the video. If you did, I can't thank you enough. I'm really enjoying making videos like this. I hope that they're useful. I hope they make sense. If there are things that you'd like to see in the future, or things you have questions about, or things you liked, or things you didn't like, leave me a comment. I'd love to talk to you. Remember to hit subscribe. But for now, that's all I got. Thanks for watching.